the GPU computation demand. We need accelerators for better computational power. And some examples of the accelerators are this GPU, graphic processing unit, FPGAs, field programmable gate arrays, and ASICs. ASIC is basically application specific integrated circuit. So a comparison between all of them will be more general purpose, but very less efficient when compared to GPU and FPGA and ASIC. So, but in terms of energy and efficiency, like efficiency meaning performance, cost per unit is basically energy efficiency. So in terms of that, ASIC are basically the best. And when we say SoC, same chip, then we call it a system on chip or SoC. And during my PhD, I was looking extensively at the GPU aspects, GPU energy efficiency, scalability, etc. And during my PhD at Harvard University, during my postdoc at Harvard University, I started looking at the whole system holistically. Yeah, I think throughput and latency we already discussed. Just for the sake of discussion, like if I'm starting from my home to work and there are two solutions to it, car which takes 30 minutes, bus which takes 45 minutes. Car has 2 seats and bus has 100 seats. So in this case, the latency of car is 30, latency of bus is 45. And the throughput, that is basically the number of passengers that I'm carrying at a given unit of time. Throughput of the car is 2 and the throughput of the bus is 100. And in this example, the bus basically is the GPU and the car is basically the CPU. I wanted also to give a brief idea about what GPUs are and how they are different fundamentally than the CPUs. So actually CPU and GPU are designed very differently, and the purpose of this slide is to show pictorially so that we can develop some mental model of what their differences are. So first point of difference is the cache memory. So as you can see, the yellow portion is much bigger in the CPU compared to the GPU. Second thing is the GPUs have resistors. The red portion, the resistors are bigger in the GPUs compared to the CPUs. And the SIMD units, which are basically the computing cores, they are also very big in the GPUs compared to the CPUs. CPUs have control logic, but GPUs do not have any control logic. Rather, they have a thread management logic. Let's try to understand what is the purpose of each of them. Right. So first feature in the CPUs. Okay, so some of the feature, like all the features in the CPUs, basically help it to become a latency oriented device. So what does it mean? So first feature is like it has some powerful ALUs shown in the green color. So the powerful ALUs help to reduce the latency of a given arithmetic logic operation. Second is they have very big caches because the caches can convert the long latency memory accesses to short latency cache accesses. And the third part is the control. They have a very sophisticated control mechanism, and which are equipped with some good branch prediction and data forwarding techniques. And the GPUs, on the other hand, they have smaller caches, which help boost the memory throughput. And they have simple control, no need of fancy control. They don't have branch prediction. They don't have data forwarding. And second thing is they have very efficient ALUs, which makes use of many long latency but heavily pipelined cores for high throughput. And then last is so there are lots of parallel threads that are running and using all this course. So there has to be some management mechanism for managing all those parallel cores. That is why we have this. Uh, Basically, in the previous figure, we had this um, thread management logic, which helped to manage the thread logic and the thread states. Okay, to summarize, we have CPUs which are better with latency-oriented design, where latency matters for the sequential parts. The CPUs can be way faster than the GPUs if I have sequential code. But now, if I have lot of parallel code, then in that case, GPU will be a better design choice to make, because in that case, I can make my code almost 10x faster. So yeah, one of the thing is high performance computing is achieved by caching. Again, like we discussed this through the session. So I'll skip this as of now. And yeah, basically the GPUs have multiple layers of caches, just like the CPUs. Um, and the smaller and the faster cache is close to the GPU, and the larger cache is away from the GPU. And when we are designing a heterogeneous parallel computing system, we use the best match for the job. For example, we will have different varieties of processors in the SoC. For example, mobile SoC will have latency cores. For example, CPUs will have throughput cores. In this case, GPUs will have different hardware IPs, DSP cores, configurable logic cores, and on-chip memories, etc., etc. So this is best suited for AI or AR/VR applications. Another thing that helps achieve high performance computing is parallelism versus concurrency. So parallelism I can have if I have multiple resources. In this case, Coke vending machine is the resource. If I have more number of Coke vending machine, then I can serve two queues in parallel. No problem with that. But if I have just one Coke vending machine, I still want to serve two queues. What I will do is I'll say, okay, you think about the order that you're going to place, and by that time, I'll finish the transaction with the person who is standing at the head of this queue, and vice versa. So yeah, I think we can skip the details of the Amdahl's law. And yeah, basically GPU in GPU, like we have a CPU, which is again the master device, and it breaks down my application into smaller kernels. And then there is some unit called as thread block scheduler, because this yellow boxes are called thread blocks. And then these boxes here where SM is written stands for different multiprocessors. So we have thousands of multiprocessors within the GPU, and the thread block scheduler is going to take one of the thread blocks from the kernel and map it to different SMs. So I'll try to pause here and then see if anyone has any questions before proceeding. No. Okay, so next the thing is why we need to optimize the LLM inference on the GPUs, because of the high speed that the GPU offer. They can process large amount of data in parallel, and thereby significantly accelerating the LLM inference. And second thing is the efficiency. So the optimized inference here can reduce the computational cost and the energy consumption. And the third thing is the scalability. So the GPUs can be scaled to handle larger models and the workloads, like we saw in the the Google Brain example. And second thing is, before I end the session, I would like to shed some light on how has the deep learning hardware evolved over the years. So here on the x-axis, I have time, and on the y-axis, we have the complexity of every model. So like it stands for petaflops, which is a measure of the throughput, and multiplied by days of training. So the complexity of the deep learning model has actually increased dramatically over the time. And for example, only from ResNet to BERT in 2 years, or from BERT to GPT-3, BERT came in 2018, GPT-3 came in 2020. It has increased by almost 1,000 times. So the ability to successively train the complex models is now heavily dependent on increasing the hardware performance. Again, this figure shows that like how the single GPU performance has scaled up over the years to meet the demands of the deep learning. So the GPU inference performance here, we can see that like on the y-axis, it's again throughput, integer 8 tera operations per second. The graph on this basically shows the different generations of GPUs, the model number, and the green one shows the absolute number of the throughput that we are, or inference performance that we look at. So here the GPU inference performance has increased by about 317x, which is more than doubling if we take an example of 2012 to 2020. So Kepler to Ampere, like it has increased by more than 2x per year. And this is now called as Wang's law. And that became possible because of various different factors, such as we had different data types like int8 data types. Remember the figure that I showed, which had about 8 GPUs in my lab system. So each GPUs need to talk to each other through a very efficient channel. So some work has been done from 2015 to 2016. NVIDIA introduced something called as NVLink, which enabled faster GPU-GPU communication. Then again, clusters of GPU, they connect to each other using the NV switch. And then we had support for the different data types in 8 cores. And then we had tensor core support for sparse data computation. So many of the AI models, they have sparse data. So for handling that, we need the tensor core support. So yeah, I'll basically end my talk here that like there are lots of hardware advancements for accelerating deep learning models on the GPUs. And there are also software advancements that have aided this progress. And the reason why the efficiency or the energy efficiency matters a lot is again the same GPUs taken on the x-axis. If we see the blue part is good, like the performance has increased over the years. But the problem is the orange line. Here, the power consumption of those different generation of the GPUs has also increased significantly. So yeah, basically, like there is with the increase in the high performance demand, there is also significant increase in the power consumption, and this is because of technology scaling, increasing number of cores, and other microarchitectural changes. So yeah, basically that's a very like important challenge that the present day GPUs suffer from, both energy and performance challenges. So yeah, for developing the AI models, we also have to take the scalability, the AI infrastructure challenges, energy efficiency really, really seriously. Yeah, I think I have reached the end of my session. Sumati ma'am, is there any question for me?
Any question from the participants?
Okay, I think Deepalika ma'am is asking what are the biggest ethical risks of using AI generated content.
Yes, ma'am. My question is there. Can you hear me? Devasri ma'am? Ma'am, are you there? Madam, can you hear me? Ma'am, can you hear me?
Yes. Hello.
Ma'am, can you hear me?
Yeah. Yes. I am able to hear you.
Yes, ma'am.
So yeah, one of the ethical risks for AI generated content in ChatGPT, like ChatGPT in academia, I think one of the audience asked this question. So one of the challenges that I face is I teach computer architecture. My background is computer architecture, and ChatGPT is not trained with lot of computer architecture data, right? So whatever answer it gives is very wrong and absurd answers. And second thing is the copyright infringement does not when you are having AI generated text, you don't know whose data it has taken inspiration from, right? So that's one of the major challenges. And I think the AI tools, because people have started using AI tools a lot, many papers in the journal and conferences are getting retracted because of taking generous aid from AI without putting the original contributions in the paper or in the work.
Thank you so much, ma'am. We are very much delighted to have you with us. And actually, it is very insightful session. You have explained the GPU and CPU in a clear-cut manner that will be very effective for the research scholar. Thank you so much, ma'am.
Thank you, ma'am, for having me.
Thank you, ma'am. Okay, ma'am. Dear participant, do you have any query to Devasri, ma'am? You can put it in the chat box. Madam, I think there is no query related to GPU and CPU. So, ma'am, thank you so much, ma'am. By this, we conclude our session. So, next tomorrow, our first session timing is from 6 to 7:30, and next session time is from 7:30 to 9. Okay, thank you, everyone.